Guys, welcome back to my YouTube channel. Today we'll be dealing with bend bricks. This is Mechanotechnics N6. This is our introduction, and then this is a new chapter for us. We don't know nothing about bricks for now, but N6 level will be introduced to bend bricks. Right, we have the bend bricks here. So let us see what is going on here. And I advise you guys, if you have not subscribed or if it is your first time watching my video, please subscribe, right, and click that notification bell so that you'll be notified whenever I post a new video, right? So general introduction, they have given the basic idea of brick breads is based on the interaction between two masses. One mass is at rest while the other mass are predetermined angular velocity. The function of a brick is to bring the moving angular velocity to rest. We know that. Slipping between the surface in contact unavailable because of the high velocity this surface move at when the bricks are applied. Okay, will increase the temperature because of the energy that is released. The following elements is brick design applied. The applied force, torsional ability of the bricks, the energy loss, and the temperature increased. All right, now we start now. I think bend bricks. Two types of bend bricks are used: simple bend bricks and the block and bend brick, which we'll discuss in this section on blown bricks. Okay, now we'll be discussing about simple bend. For today, I'll go through with this simple bend, right? So here it's our structure. Let me just zoom in so that you'll see what I'm talking about. We have given here our this is our bend. I want you to notice something, guys. Let's you check here from here until there. From that area we have what did our contact angle there. We have our theta there, right? As you can see that, right? So here I want to notice here we have T1, and then you see the arrow is facing in that direction. Here we have T2, and then the arrow is facing in that direction. I want to check something. This arrow that is doing like that, you see this arrow represent the rotation. That means it's rotating in this direction. I want to check something. As it's rotating in the direction, you see T1. T1 will go in the directional rotation, will be applied in the same direction of what? Of rotation. T2 will be in the opposite. Check T2. You see the arrow of T2 there. The arrow of T2 is going in the opposite direction of the rotation of the motion. T1 goes in the direction of motion of the rotation of the brick band. Then this one will T2 will opposite direction of the brick band. Right, this is what I wanted you to see there. Right, this is a rotation. You see it here. We have T is going. You see it here. We have that T2 is going that. You see this direction. So this is continuing like that. It's going in the direction of the rotation. This is T1. Then the brick band is rotating at that direction. T2 will be opposing. Will be going in that direction. Will be opposing the direction of what? Of rotation. Hopefully you saw that, guys. You saw that. So as you see this, here we'll have a force applied. We'll talk about that. On the pivot, we have the pivot there. That will be our force applied there. All right. So the theory applicable to the flat belt drive. The theory applicable to the flat belt neglecting the centrifugal force applies also to the bend bricks. You see what we've learned about the tensions we'll use here. The example here, tension ratio. Note the tight side is T1. Always we know this. It's always T1. Tight side is always on a T1. We remember this since being pulled on the drum is being pulled is T1. When rotating the drum is reversed T1, and T2 will be changing direction. We'll see, as you have seen there, we'll see about that. Then what we know, what is important again, is to know that tension ratio. You'll still remember T1 over T2 is equals to E into constant friction over what the contact angle. Another thing you're supposed to understand, contact angle is here, guys. Let me check. Is between the tension where it is starting, is from the center until where the tension starts here at the end, like that. It goes like this till the where you have the tension is the distance between those. If the tension start like that, that means will be from the center until there. That will be our contact. You'll see that the angle there. So fine. We remember this. Okay, example on the bent bricks here. We've given an example. One says a bent brick in figure 3.2 has the mass of 20 kg, is attached to the end of the beam. The diameter of the brick drum is 750 millimeter. The coefficient of friction is 0.25. The angle of contact is 220. Says here, calculate the greatest torque that the brick can hold. State which direction of the drum must try to rotate to achieve the torque. All right, okay, it was fine. So it's what we are given here so far. Then here is our figure there. This is the figure that we are given. You understand? This is the figure. If I decide to rotate this drum in that direction, that means T1 will be acting. If I rotate, will be acting in the direction of rotation of the drum, but T2 will be opposing like that. This will be T2. If I rotate again this drum at like this, then T1 will be at this direction, T2 will be opposing. This will be T2, will be OT, this will be T2, will be opposing. You see, we'll discuss about that. Then A is a pivot. So this is what there we have a force. This is just a beam. So we can break this structure into some beam stuff. Let me change this color. I dislike it a bit. Okay, it's fine. Black. There we go. Now I want you to bear with me here. Let's say now if we calculate now, if we can calculate the torque exerted when the rotation, if we when the rotation is clockwise. Okay, where is clockwise like this? If you've given, you can say here we have. Let me grab our horizontal stuff here, ruler. Okay, it's fine. Let me do like this. Goes like that. This is our beam. Then here. You can call this F, the force there. Then here have point A, point A there is the pivot. I can call this A like that. Then guys, I try and draw it. Let me try and draw some dark or some circle there. You see, there it goes. It's a drum, right? It's a brick drum. All right, we have something of this nature. Then clockwise, talk to the executed when rotate clockwise. Here is the clockwise, the arrow. Our drum is rotating clockwise. So okay, from there, yeah, what here is rotating. Remember, from this point here, you see what happening. If our drum if is rotating like this, T1 also will be pointing in that direction. That means this side the one that will be putting that direction will be T2. This will be T2. T2 will oppose the direction there. This will be T2. This will be T2. Will be acting in the opposite direction of the drum. You see the arrow. You see the arrow is going like this. T2 must acting like that in the opposite, like this. T1 must follow the direction of this arrow there. Okay, that means here we'll have T1. Understand, this will be T1. So this is what we have, guys, so far. That will be T1. And also check. Let us, we are drawing this according to this drum here given. We have some slanted high, some slanted there, and I've drawn this, and then I've drawn this. Then is slanted there. Since it's slanted, let me slant it a little bit like this. All right. We have 90 like that here. You see, we have 9. We're drawing the same structure like this. There is our force. We have that. Now we are just choosing the direction. We have not given the direction, remember, of rotation. If we are not given, we can start by taking clockwise. Also, you can rotate the drum anti-clockwise. It's up to you. Right. It's up to you which manner you would like to rotate your drum, your brick band. It's up to you, right? So you start by rotating if you're not given the rotation. So this will simply have, this will be T1, this will be T2. All right, so calculating the ratio T1 and T2, calculate for this thing, guys, that we've drawn here, for these guys that I've drawn there, for this rotating. When I'm taking the rotation, I took the rotation clockwise because you're not given the rotation. I'll take it clockwise first. We'll start like that. So we'll calculate what? Start by calculating the ratios. We don't know the ratios, isn't it? Don't know the ratios. And then, by the way, we know that the distance from there at the pivot till there is 605, right, millimeter. So I can also write the distance there until there where the force is acting. There is 605 millimeter. Those are distance, by the way. Again, as you can see there. Then this one is 100 between this is 100 millimeter. The smaller one, this the slanted one, this is 30. That is 30. You'll have 30 millimeter for the slanted one. This one is 30. This is what we have there. What done right. So the way what we start by calculating the ratio T1 and T2. We know that T1 over T2 is equals to E over coefficient of friction multiplied by contact angle. All right, isn't it? Okay, we come E. What is our coefficient of friction from the equation here? 0.25. Contact of angle is 220. But remember, we use this in what? In radians. In radians. So this is 0.25. How do we divide this? Will be 220 degrees divided by 57.3. You understand that? We can put it here same time into 220 divided by 57.3. If you convert this, then what can we have? They will have 2.6112. Then this obvious is T1 over T2. Then you can multiply it like that. You'll have, therefore you'll have T1, you'll have the T1 to be equals to 2.612 T2, just like that. Right, this is T2, the ratio. That is the ratio. You have this T1, it's equals to this actual there. On your beam we have T1 now here. This whole T1 here that is acting there, it's equal to all of this stuff. 2.612 T2 is this force is acting upwards. As you can see, is acting upwards. It's acting upwards. You see the air, it's acting upwards. Is T1, also T2 is acting upwards. So you apply the beam, the moment. Now you can take the moments, right? Taking the moments about A here, the point pivot here about A. I've called this A, about A. I can say that it's A. Taking moment there. If you can take the moment, or should I grabs? Let me grab this diagram down so that you'll see it clearly. Or let me copy it. I'm taking like this. Then I adjust this diagram here. You'll see what is going on. Let me reduce this in size a little bit. Alright, this is what we have. So that is our beam. Take a moment about A. You can say take a moment. Take the moment now. Moment about A. So here it's A. I've shown. Let me do see the color there. It's A there. So yes, if you take sum of moments, clockwise moment, sum of clockwise moment is equal to sum of moment anti-clockwise moment. Okay, now you remember this A is the same as what is take moment about A. We have T1 here, it's T1 here. T1 is here at the end, must be multiplied with this distance there. Here is the distance there. You see that distance 30 from there, and from here until here is 30, the distance there, right? Distance there will be 30. Remember, it's in millimeter, will be multiplied by 0.03, right? Plus, now taking the moments about clockwise, which one again is acting in the clockwise form. This will rotate at that direction. Also F will cause it the beam to rotate the direction F, plus F multiplied by the distance there. What is distance? Is this one, 600, and distance from A until here is 605 millimeter. This is the same as 0.605, right, meter. Then this will be equals to T2 multiplied by what? Here is T2. The distance here between T2 and A here is simply 100, but remember it's in millimeter, must be in meter, will be 0.1, like this. Then it's a matter of what now? Matter of maths. It's a matter of maths here. It's a matter of maths. But it's a matter of maths. Remember, T1 is equals to that, so no problem. Now it's a matter of mathematics, right? T1 is this, guys. T1 is equal to that. That means in the place of T1, we'll replace with this there. In the place of T1. Alright, let me just copy that. T1, we'll substitute that here, because here T1 is the same as this from the ratio, so we'll substitute that. The space of T1 is the same as like this, the same as this from our ratio, multiplied by 0.03 plus 0.605 F is equal to 0.1 T2. Then let's maths, these are like terms T2, so apply the math. This is 0.612 T2 minus 0.1 T2. Take that would be negative 0.605 F, right? This is what we had, isn't it? Okay, though there's some interesting thing. What about F? Okay, F, we've given the mass here is 20, but force is equals to mass multiplied by what? Gravity. This will be 20 times 9.81. The force there, this is the same as this force is 20 times 10 to the power of 9.81. This is what we have, isn't it? So do not do this first. Remember, this must be multiplied there. This will be 0, this will be 2.6112 multiplied by 0.10, 0.03 T2, like this, right? First, let's see what we have, plus 0.605 multiplied by, this is just a value, same as 20 20 watts we have there. 20 multiplied by gravity. Remember the mass they've given, force is mass multiplied by gravity. 20 times 9,81. We have 0,1 T2. So here, punch this, punch that. Let's check. Well, the cookie is crumbled there. Here we'll have 0,07836 T2. It is not a final answer. Plus, multiply all of these now. 0,6 0,605 times 20 times 9,81. That must be 118,7 0,1 T2. Now it's a matter of maths. Here we have one. It's a matter of maths now. The matter of mathematics. We have 1,7 be 0,1 T2 minus 0,0078360. You take this to the other side, we'll change the sign. Then here it's a matter of maths. These are one thing. Then we have 118,7. Then this is the same as you add this, or you can simply divide with same time. You can say simply say here 118,7 straightforward, divide by 0,1 minus 0,07836. This is equals to T2. Then if we punch this, what will be T2? Right, T2 will simply equals to 5,485 newtons. What about T1? Now, what about T1? We know that T1 is 2.6112 T2 from that ratio, from this ratio here. Then now we substitute 2.612 into 5,485. Then T1 simply equals to 1,4327 newtons. So we have this now. When you rotate, then what is torque? Said calculating the torque is we wanted to calculate the torque when you rotate this clockwise. Torque is T1 minus T2 multiplied by R. All right, then T1 it's 1,4327 minus T2, whereby T2 equal to be 54. Here it is there, 5,485. The radius of the drum, what is the radius? 700, and divide by 2 would be 3 what, 375, whereby in meter will be 0,375. Multiply this by 0.0375. Then the torque simply 3316 Newton meter. Remember, when we're talking about clockwise rotation, we're not dealing with clockwise rotation. But what about anti-clockwise? What about anti-clockwise? What about anti-clockwise now? What about if we're rotating it anti-clockwise. Let's find the torque now. If we're rotating it anti-clockwise, we'll take the moment about A is 9th. You simply just switch the values around now. Where you see T2 will be T, with the method of switching the values. You switch around. It's only that, there's nothing else. You just switch around, switch the values on. Taking the moment about this, you see you'll switch now the values. Here is T2 will be T1. Where you see T1 will be T2. You just switch the values around, and then you switch this will go to that side, this course will go there. You can switch if you want it fast, or you can start afresh again, taking this diagram and rotate it. You can start, but just switch around anti-clockwise, or you can take this diagram again and take the moment about A. But so far you're supposed just to switch everything around. It's the one and the same thing, just switching everything around, taking moment about A. If you take the moment about A, T1 will be T1 here will change. Now we rotating it anti-clockwise. If you rotate this at anti-clockwise, this you switch now, this will have now T2 at this side, then this side will have T1. Understand? And then we know that T1 it was 2,612 T2. So if it's rotating like that, to change, so this will simply cause T1 multiplied by this distance there, T1, this distance of 100, which is 0,1. Right, you can write sum of clockwise moment equal to the sum of anti-clockwise moment. So yeah, T2 rotate clockwise, this one will rotate that side, T1 multiplied by 0,1 will be equals to T2 multiplied by this is what is 30, 0,03, then plus again the force here, force multiplied by 0,06 multiplied by 605, like that. Is in it, then this T1 here, this guy there, by 261 to T2 times 0,1 is equals to T 0,03 T2 plus the force there is 20 times 9,81 times 0,605. So yeah, here we'll have multiply this same as 0,1 multiplied by 2,6112, 0,261 T2 is equal to 0,03 T2 plus 118.7, then this would be 0.0261 T2 minus 0.03 T2 is equals to 118.7. Therefore, we find T2 is simply 118.7 divided by 0.0261 minus 0.03. The T2 is simply equals to 513.4 Newton. Then T1 would be what? 2,612 multiplied by 513.4 will be equals to 1341 Newton. So the torque now, when you're rotating anti-clockwise, the torque is T1 minus T2 multiplied by R. So T1 is 1341 minus T2, which is 513.4. The radius of the drum is 0.375. Then the torque simply equals to 310 Newton per meter. So this is what we have. So the greatest torque, let's check where is the greatest torque now. Here you have 310. Then the other, how it was this one. The greatest torque is this one when you're rotating clockwise. The greatest torque, because they said we should determine the greatest torque, hold state which direction drum must rotate to achieve this. To calculate the greatest torque that the brake can hold, state which direction that must rotate the greatest torque. So the greatest torque here must be when we're taking clockwise. The greatest torque will develop will be exerted or developed, will be applied in the clockwise direction. So yeah, that is it, guys. So thank you for watching, guys, and please do not forget to subscribe to my YouTube channel and click that notification bell so that you'll be notified whenever I post a new video.